an overview of what we'll do today. My plan is to start with a little bit kind of wrapping up some of the gravity stuff. There was one of the questions on the reading quiz that a few people were struggling with, so I wanted to kind of go over an example and just kind of talk a little bit more about that. And then we'll kind of switch into this Earth-Moon system, and most of today will be devoted to playing around with Earth-Moon models. So you'll work in groups. Usually we would have nice equipment, very fancy equipment for you guys to make Earth-Moon models out of, but we're gonna have to kind of go with what you have around you, but it can be really, so we'll kind of, as we go through that, hopefully in your groups we can find a way to try to model the Earth, Moon, and Sun as best we can. And then when we wrap up, I want to talk a little bit about a few changes that I've made to my plan moving forward, specifically, especially about Tuesday, and then also a little bit about homework. So that's kind of my plan for today. Does anyone have any questions about anything before I get started? If they are about homework, like I said, I will save 5 minutes at the end of this class to talk about that. Okie doke. So let's get moving. So the first thing, just to go over a little bit, I didn't really touch on this, but when we talk about gravity, there's kind of two different things we can think about. We can think about an object's mass, or we can think about an object's weight. So the mass of an object is going to be the same no matter where it is. It doesn't depend on gravity. It's just how much stuff is in that thing. So how much the mass of this coffee cup is going to be the same whether it's on Earth or it's on Jupiter, because it's just like how many atoms are in my coffee cup. Whereas weight is going to be dependent on where you are. So weight is how strong the force of gravity is. So when you get on a scale and you measure your weight, what you're really measuring is how much gravity is pulling you down. You're measuring the force of gravity on your body. So that changes depending on what planet you're on, or even where you are on Earth. If you go up higher, your gravity is slightly, your weight is slightly less. Not much, not a measurable amount, but very slightly. And so I kind of threw in this little gif of an astronaut falling down on the moon, because what you can see is that he's experiencing different gravity. The mass, his body's volume has not changed, but because he is on the moon and not on Earth, he's bouncing around and falls over. We know it's a dude because there haven't been women on the moon yet, so I can say man. And just as kind of a reminder, we have our equation for the force of gravity, which is this big G, that universal gravitational constant, which is a number that Newton found, multiplied by the mass of your two objects. So this might be your mass and the mass of the Earth, whatever you're trying to measure the force of gravity on, and then divided by the separation between those two objects squared. And we also can measure the acceleration due to gravity, which is usually shown as a little g. And that's just equal, it's the same thing, but now your mass is taken out of the equation. So it's universal gravitational constant, what you're being pulled towards, the mass of what you're being pulled towards, divided by the separation between the two masses squared. So we can use that equation to kind of figure out what your mass will be on other planets. So this was kind of what the homework question was like, and I'm going to try to rotate my computer, my funky standing desk, so you can see me with a whiteboard, and I will stop my screen share in a second. But the idea is we are going to magically fly in our infinite probability drive spaceship to Magrathea, which is another one of my nerdy references. This is Hitchhiker's Guide to the Galaxy. And so when we get there, we want to figure out what our new weight will be on Magrathea. We know that Magrathea has a radius of half of Earth's, but it has twice the mass. So we have 2 times the mass of Earth, but only half the radius. So we're going to use that to figure out what our new weight is. So we can do that by finding the force of gravity. So I'm going to stop my share for a second so you guys can hopefully see me a little better. And what we have is we know F, G, hopefully this is semi-visible, is equal to G, M1, M2 over R squared. Can folks see me, hear me okay? I think I see some nods.
Yeah.
Awesome, thank you. So we want to figure out what the new force of gravity is, our new weight, with the different masses and radiuses. So we want to figure out the force of gravity on Magrathea compared to Earth. So we want to rewrite this in terms of Earth measurements. So our mass hasn't changed. We're going to be mass 1. Nothing has changed. We haven't lost anything. We're going to write mass 2 as I said, oh gosh, I said 2 times mass Earth. And then we're going to write our radius as 1/2, our Earth squared. So now we have the force of gravity on Magrathea in terms of the mass of Earth and the radius of Earth. Knowing that our mass 1, it hasn't changed, that's going to be the same. So now what we can see, so you've got, we want to kind of rewrite this in terms of the force of gravity on Earth. So we're going to square our 1/2 and pull out our 2 to end up with Fg equals G, let me actually do what I said, 2G M1 M Earth over 1/4 R Earth squared. So the nice thing is what we can see is that this part here, this is just our weight on Earth. This is exactly the same as our weight on Earth. So now we have a factor that we're multiplying that by, and that's going to be our weight on Magrathea. So it's 2 divided by 1/4. 2 divided by 1/4 is the same as multiplying by 8. So we can write this is just 8 times the force of gravity on Earth. So on Magrathea, our weight is going to be 8 times our weight on Earth. Yes, I'm gonna go back and share my screen again. So does that, how do people feel about that? Ask me a question. Okay.
So wait, sorry, just real quick. So we don't, for like answering that question, we don't need a specific number. We just need to know that it's 8 times what it would be on Earth.
Yep. Yep, I will never ask you for a specific force of gravity. I just want to know how it compares to Earth. So if you can get the number times that G M1 mass of Earth, so your mass times the mass of Earth divided by the radius of Earth squared, that's our weight on Earth, and then whatever we're multiplying that by will be the time, how much more you weigh or how much less you weigh.
So I have a quick question.
Yeah.
Really not need to like put everything into the equation. You can just like look at the numbers and then kind of like determine what the new weight is without putting it into the equation.
So you can, it can be a little tricky, just you need to just make sure you remember that your radius is squared and you're dividing by that and your mass is multiplied just singularly. So you don't have to plug it all in. This will just, is a really safe way to do it if you want to make sure you're getting things right. Yeah. Anything else? So with that, I have two kind of concept questions for you. I'm going to launch a poll. The first one is, we're on an Earth. Some evil genius learned how to like puff Earth up. So we've increased Earth's radius by a factor of 2, but the mass has stayed the same. So I don't need to know any actual numbers. I just want to know, on our new puffed up Earth, would your weight increase or decrease? So I've launched a poll, and that's the first question. The second question is similar, but now instead of changing the radius, we're going to change the mass. So we're going to turn Earth into a giant pile of blueberries that has the same radius, but now it weighs less because blueberries weigh less than rocks. So would our weight go up or down if we decrease mass? Got about half of folks voting. And so what you can see, we kind of had a little bit of a split on our second question. So in the first question, if we doubled Earth's radius, most people thought our weight would decrease. That's correct. So if radius gets larger, your weight gets smaller. So if the separation between you and the object gets larger, your weight gets smaller. The second we were a little more confused on, I threw in the blueberry Earth thing because I think it's kind of funny, but the idea is if mass gets smaller, so if we're on something with a smaller mass, the force of gravity is going to be less, so our weight will be smaller. So that might have been, I might have made things a little funky, but I do want to point out that there was a scientist who tried to find out what happens if you turn the Earth into a pile of blueberries, and it's a pretty good article if you want to read it. Radiolab also did a podcast about it, so possibility for a podcast or article project if you want to learn more about blueberry Earth. But yeah, so radius increase, weight decrease, mass increase, weight increase. Any other questions? Okay. So with that in mind, the thing I wanted to end on gravity is just to point out that because that acceleration of gravity, if we go back to that equation, that only has the mass of the object you are on. It does not have your mass in it. That m1 disappeared in the acceleration due to gravity. What that means is that all objects fall at the same rate. So to illustrate this point.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Sorry about those very high-pitched beeps at the end. But the idea is, in the Apollo mission, one of the things they did is they tested Galileo's theory, dropping a feather and a hammer. They fall at the same rate on the moon. because the moon doesn't have an atmosphere. So gravitational acceleration doesn't depend on the mass of your object, only depends on the mass of what you are being pulled towards. So switching gears a little bit, we're gonna hop over to talking about the Earth and the moon. This is just some kind of basic facts. I will never ask you to regurgitate basic facts, but it's good to kind of think about these things for a bit. So don't worry about memorizing any of this. I think that's terrible. But the idea is I've shown you both the, so the Earth and the moon to scale radius-wise. So the moon is on this upper image here. So you can see the moon is much smaller than the Earth. And then at the bottom here, this is the Earth and the moon to scale with the separation. So pretty far apart compared to their actual sizes. The moon is about 1.3 light seconds from Earth. So what that means is that it takes, when you look at the moon, you're seeing it as it was about 1.3 seconds ago. It's also about 384,000 kilometers away on average. The moon, just like all the planets, is going on an elliptical path around the Earth, but it's pretty close to circular. So that 384 kilometers is our 100,000 kilometers, sorry, is the semi-major axis of the moon's orbit. It's not the fixed radius. That's why I said kind of iffy. It takes about a month for the moon to go around the Earth, and that's where the word month comes from. So you can kind of remember that. It's 1 moonth. Sorry, have to make a bad noise there. That's the only time I'll do that. So the orbital period for the moon is 1 month-ish. So now we get to do our little activity. I will put you guys in breakout groups. And oops, sorry. This will be our first activity under your assignments for day 4. It's here, and like I said, if you have any kind of vaguely circular objects, that would be great. If you don't, if you can like tear out a piece of paper and you can crumble up one and have it be bigger than the other, that could be your Earth and moon. Whatever works. Also, if you have a light source to be the sun, that's great. If not, if you can just even use the sun. We're gonna have to kind of MacGyver this since I can't pass out materials, obviously. But whatever you have, and if your group can make one model together, that's also fine. So whatever works best. So